Hello and welcome again to another edition of Lost in Science. It's half an hour on your radio where we talk about sciencey things.
All things science.
All things science.
Every science.
My name's Stu, and this week I'm going to be talking to Tasha Stanton from the University of South Australia about chronic pain and how do we measure chronic pain, and why do some people say they're in pain when their brain says they're not, and why do some people say they're not in pain when their brain says they are, and how we potentially try and fix it. Chronic pain is a huge medical problem. So, Manisha.
Hi, everyone. So today I'm not talking about pain, but I'm going to be talking about birds. Seem to talk about birds a fair bit. But I'm talking about how they're different in the city and how they're different in the country, and if their aggression is related to where they live and things like that.
So do city birds get more aggro than country birds?
Yeah, basically. Do they got road rage? Do they know how to just, or like maybe
too much
the rural
air
birds,
traffic?
Yeah, exactly. The rural birds can just kick it back, relax, really, take the best parts of the day, take time to smell the roses.
And and Chris will be speaking to Julie McInnes from the University of Tasmania about collecting and analysing albatross poo.
Oh.
So more birds.
Yay, for sure.
Trying to figure out what albatross eat and understand whether their diet's changing as a result of climate change.
Ooh.
So more of that later in the show. Stay tuned. With me, Tasha Stanton from the University of South Australia, and Tasha researches pain, and we're going to talk to her a little bit about what she does research. Thanks for joining us on Lost in Science, Tasha.
Oh, my pleasure.
So you are a researcher in the phenomenon of pain and chronic pain. How did you get into that for a start?
Yeah, it is a bit of a convoluted story, but I actually originally trained as a physiotherapist. So I worked with people actually that had injured their backs or other parts of their body at work and had needed to receive treatment for their pain. And what I found was that I just really had so many questions. There were so many things that I wasn't quite sure how to help people, and there wasn't necessarily the research out there to guide me in how I might be able to help people. So I think curiosity kicked in, and I gave research a go, and I thought, I'll do a master's, see how I like it, and I fell in love. And then I feel like I've had been given such great opportunities to continue focusing on my science and looking at my research into chronic pain, and that has led me to do my PhD at University of Sydney, and now do a couple of postdoctoral fellowships at Neuroscience Research Australia in Sydney, as well as at University of South Australia in Adelaide.
So you went from I guess, helping people physically with their pain to looking at their brains. Is that?
Yeah, that's a fair assessment, exactly. I think that was really what intrigued me when I was working as a physiotherapist, is a lot of what I had been taught had really been to focus on the mechanics, focus on what could be physically causing person's symptoms and the pain that they felt. And there were so many people that you just could not attribute what they were feeling to mechanics or to what, let's say, a scan showed about what was going on in their back. And that absolutely piqued my interest and just made me think, gosh, there has to be something more going on here. And that's really when I started to focus on what role the brain and changes to our nervous system in general might play in causing those symptoms to be exacerbated in people that have chronic pain, and for those symptoms to stick around when tissue damage has already healed.
So is there any link between the neurological perception of pain and the psychological state of the patient? Do you look into that at all, or?
Yeah, that's a great question, and I think it's not a super easy answer in the sense that if we look generally, we do know that if people, let's say, have depression or anxiety, and quite significant ones, they're more likely to develop chronic pain. But a lot of people, when they get these awful chronic pain conditions, they quite understandably develop these symptoms of depression and anxiety. And from a level where we look at how they interact, what we understand quite well is that things like that we would call psychological aspects of it, so things like anxiety, depression, they have real physiological consequences on our systems. So it means that it literally changes how nociceptive or it could be tissue damaging or danger messages are being processed in the brain and the spinal cord. And that literally then changes the experience that people often have in terms of their experience of pain.
So when you look at a patient who's experiencing pain, are there ways of objectively measuring how much pain they're in that, you're not just taking their word for it? Is there any way to measure what sort of sensations are going to their brain?
Yeah, we try to always answer that question using imaging, but that is a problem as well, because if you think about imaging the brain, and what we do then is we look for if there is increased activity in different levels or different areas of the brain that correspond. But the thing is you're always using a subjective rating of pain, because that's actually what we look at, is what areas correspond to, for example, increased reports of pain intensity, which areas also increase in activity. So really, the subjective experience validates what is going on in the brain. Some experimental research that's going on is looking at, okay, if we give someone a stimulus, let's say we put a very hot probe that hurts on their hand, if we just establish that, say, yes, that does hurt, that results in pain, what they do is they're trying to train computer algorithms to be able to detect, based on brain activation only, whether or not someone is in pain or is not in pain. And that's I think it's a very interesting idea, but at the end of the day, it's not an accurate test or an accurate way to look at it unless we actually know that the stimulus we're providing is causing someone to experience pain. So we go a bit in a circle there, because I think there sometimes is a push towards, let's get an objective test to determine whether or not people, this is real or not. And I think that actually goes down a bit dangerous route, because we know so little about what's going on, and we are only beginning now to understand, I think, or I guess appreciate the true complexity of the experience that is pain. That it's much too early days to be able to say that we can do this objective scan and tell whether or not a person has pain.
I guess it's a bit dangerous also to say, well, you say you're in pain, but we're not going to take your word for it because the computer says that you're not.
That's exactly right. Exactly right.
I guess the patients come to seek medical attention because they are in pain for some reason or another. So you've got to sort of help them out with that.
That's right, and I think that's a really important point, because if we look back even 20, maybe 30 years ago, conditions such as fibromyalgia were really thought to not be real conditions. And that is an awful thing for patients to go through. They're having these terrible symptoms. They're feeling very fatigued. They basically feel like they have the flu most of the time. They're going in, they're trying to get help, and they're being told that, there's nothing wrong with you. This isn't real, like this is all in your head. And it's funny because from a neuroscientist point of view, we argue, yeah, indeed, it is all in your head, but not the way that you think. It's because any sensation that we have, touch, pain, itch, they're created in our conscious brain by using information that's coming from the periphery and then creating this conscious sensation. So, well, I think that statement traditionally has quite a lot of stigma attached to it. From a neuroscience perspective, it's actually incredibly accurate.
So just can you just explain what your current research involves and maybe a little bit about what you've found?
Yeah, of course. So what I'm looking at is trying to understand a bit better the link between how our brain processes information about our body, how it knows, where it is in space, where you're being touched, and how that might relate to experiences of pain. So where this kind of comes from is because what we see in a lot of people that have chronic pain is that they have these altered perceptions of their body. So I've done some work in osteoarthritis showing that they're very poor at knowing where they're being touched. So when touch information is processed by the brain, it doesn't seem to be processing that information very well. They're very poor at knowing where their body is located in space. And it seems that the brain maps that code for movement planning and movement coordination, they also aren't working very well. And when you get them to do a task where they actually identify, what is the true size of let's say, your painful hand, they will be significantly different, make a different choice than what healthy controls will choose. They think their hand is significantly smaller than it is. And so what's quite intriguing then is that we know that all different information from various sources, so touch, movement, from nociception, which is the danger signals coming from the body from tissue damage, all those are combined together to give us this sensation of our own body, where it is, and it's how we're able to move in the environment. But because all that information is combined together, it raises the possibility that we can use changes in information from one source to actually then modulate or change information coming from another source. And so what I mean by that is we use visual illusions and see what effect they have on pain. And so my research at the moment has been looking at what is the effect of visual illusions that make it look like your knee is significantly longer and growing and stretching than it truly is. But what's quite potent is because we're using real-time video and we're manipulating this in front of people's eyes, it's very compelling because you're literally watching your own knee change. And what we found with that is that altered vision of your own body appears to be analgesic. It reduces the amount of osteoarthritic pain that people feel. And this is quite interesting because we actually see evidence for this when we use experimental pain paradigms. So when we burn someone on the arm and we make the arm look bigger, that actually hurts more. Whereas if you're making the arm look smaller, it doesn't hurt as much. So it suggests that actually how we, the way that our senses interact is an important feature and might be able to be used to modulate that experience of pain and potentially be an analgesic treatment.
Wow. So if I accidentally hit my thumb with a hammer, if I use some sort of lens to make my thumb look smaller, that will make it hurt less.
Theoretically, yes. And it's really interesting because there's another condition that it's quite a rare condition that sometimes occurs after a limb fracture. And in this condition, when you make the arm look smaller, the hand look smaller, while you're moving that one, actually both pain and swelling decrease. So isn't that cool?
So it's not just psychological, it's a physiological effect.
That's exactly right. And that's really what I'm quite intrigued in studying, is understanding the physiological effects of this, because it's not, we use a lot of controls in our experiment to try to make sure it's not just because, it's a cool machine or we're playing around or we're distracting people. We really want to tease out what is going on in terms of the way different areas of the brain are interacting with each other that might be causing or producing this analgesia.
Well, that's a whole new approach to pain management that's pretty novel as far as I know.
Yeah, it's certainly the idea of using different senses to modulate pain. It really has been quite recent, and we're only just starting to understand how these different features combine and interact, because what we are showing at the moment is short-term effects. And in order to be able to figure out how to create longer-term effects, we ideally need to know how this works. What is the mechanism behind this?
And I guess that would be the next phase of your research.
Yeah, exactly. So I've got a fair bit on my plate, but I'm quite excited about it.
Okay, well, Good luck with finding this out. I mean, I know pain and pain management is a huge issue for medicine
Absolutely.
in as far as, the most effective treatments we have is using drugs for pain control, which don't always work, and they have addictive problems and all that sort of thing. So finding new ways to deal with pain management is a huge direction for medical research to go in, and I'm very interested to hear your findings in the future.
Oh, thanks very much. And I agree with you. I think, chronic pain, people don't realize 1 in 5 Australians have it. And so chances are you probably know someone who does. So oftentimes this stuff it hits really close to home.
Well, and you've got a good chance of developing it as it seems to increase with age too.
Yeah, that's right, unfortunately.
Well, look, thanks for joining us, Tasha. That's been really interesting to hear about your research, and I hope to talk to you again sometime on Lost in Science.
Great. Thank you so much, Stu.
Across Australia on the Community Radio Network, you're listening to Lost in Science.
So, urbanization, it can have a number of impacts on wildlife. It can change where they live and where they forage, how they find mates, and how successful they are at raising offspring. And one of the big challenges with urbanization is that there may be a lack of resources available. So for individuals, it may be more essential for them to become more territorial or aggressive. And so basically, there's been a heap of studies that are done to kind of determine what really leads you to live in the city or nest or den or whatever in the city versus doing these things in the country or in less urbanized areas, and how these environmental factors or maybe even physiological factors can change because of where you're nesting. With aggression, it may sound simple because basically you're trying to be aggressive to maintain your share of the food or the territory. But it's also important to remember that this aggression, it comes with a cost. So not only are you constantly putting yourself under stress, but you're putting yourself into these physical altercations, which could result in you becoming injured or even die as you're trying to be territorial and as you're trying to defend your nesting area. So there's a number of studies to look at aggression, particularly in birds. Actually, I've noticed that a lot of these aggression studies tend to be in birds. So researchers have been examining the difference in aggression that's displayed in wildlife and looking at how this relates to their health and their fitness. And one such study, it was just recently published in Biological Letters, and it compares aggression in the song sparrow in the United States. And the study, it was conducted by Scott Davies and Kendra Sewell at Virginia Tech, and basically the authors set out to see if this difference in aggression expressed in the urban and rural song sparrow populations was either due to their plasma testosterone levels in the male or if it was due to an environmental factors. So they chose to look at conspecific neighbors. And so that's basically the density of other song sparrows that are nesting in their same area. They basically went out, tested the aggression in two different populations of the song sparrows. They tested the aggression by basically putting up a decoy and then just taunting the bird and seeing what the bird would do.
So they were teasing the sparrows to see what their reaction would be.
Exactly. So basically, putting up a threat and then seeing if the sparrows would react at all.
Take the bait.
Yeah, exactly. So they made three main conclusions. First, they determined that, like in other studies determined about, like other studies on birds, urban birds are more aggressive than rural birds. But then their next two conclusions were a bit interesting. First of all, plasma testosterone didn't actually differ between urban and rural populations. So they were, in terms of physiology, they had the same sort of aggressive protein running around, or aggressive steroid running around. And then finally, there were actually fewer conspecifics in urban areas than in rural areas. So that suggests that there's less competition in the urban area than there is in the rural areas. that's the interesting part of it, because the results are just counterintuitive. So rural and urban birds don't differ in their testosterone expression, nor do the urban birds have higher competition. So why are they more aggressive? So the authors they gave a few ideas as to why this might be, and the two that I thought seemed to be the most have the most foundation were that either we're viewing urban areas in the wrong light. We want to say that urban areas are taking away the habitat and like really destroying their space and things like that, and it's not this pristine area. But at the same time, because of human alterations of the land, we are perhaps providing a better habitat. We plant trees, we plant these gardens, we leave out food materials. So maybe it's better to live in urban areas because these sorts of things are just more accessible. So if you can have a successful brood in a city, you've just got all sorts of resources available to you, and you don't have to work for those resources as much. And then the other sort of unexplained result was the competition, which I think it could also be reflected in the competition at establishment. So if a bird is more aggressive, it could be possible that the bird's always aggressive. So it's not just when they're trying to defend their territory, but even when they're just establishing their territory to begin with. So maybe the urban birds don't have as many neighbors because they basically fought off all their neighbors when they were first making their nests, and now they're reaping the benefits of it. So that aggression has led to the situation in which they are now, if that makes any sense. But it's really hard to say, because you don't really know which way the relationship's playing out. It's kind of like a chicken and an egg situation where you don't know what's come first. Is it the aggression that's come first, or the urbanization, or
a sparrow and the egg situation, really?
Exactly. Yeah, exactly. Anyway, so for at least this system, the question remains unanswered.
Listening to Lost in Science. My name's Chris, and I have on the line PhD candidate Julie McInnes from Tasmania's Institute for Marine and Antarctic Studies. Now, she's studying albatross, but the way she's doing it requires a special sort of dedication. Julie, can you tell us what it is that you do?
Oh, hi, Chris. Yeah, so we're looking at albatross diet using DNA in their poo. So pretty much this involves going out and collecting a whole lot of albatross scats to find out what they're eating.
Right, why are you collecting poo or scats, if you want to use a technical term, I guess?
So we're collecting poo because it actually provides a non-invasive way of looking at diet. So we can go out into the colony and collect these poos, and then we do a bit of lab work where we're extracting the DNA and then sequencing it, and you can get information about the prey that they've been consuming. The main reason we're going for scats is that the birds don't need to be handled. There's very little disturbance, and it's much better than some of the previous techniques that have been done before.
So the birds don't mind you sneaking up behind them and stealing a bit of poo?
Well, look, they don't seem to be wanting it anymore. They do give you a little look like wondering what you're doing, but I guess that would be understandable if you are picking up their deposits. But generally, yeah, there's not much disturbance involved at all. I mean, we sit there quietly on the side of the colony, and then when we see a bird poo, we sneak in and collect it and then get back out again. So it's a much nicer technique. Previously, what they used to do is actually collect regurgitates from the birds, so whether that be from the chicks or from the adults. So the chicks, they vomit as a defence mechanism, so you do get these regurgitates coming up from the chicks, and from that you can get some really important information about prey through the hard parts, so squid beaks and the fish otoliths, so the ear bone that remain in the stomachs of which they can't digest. But unfortunately that denies a chick a meal, and when it's done to the adults, it involves sort of the stomach flushing, so actually causing the bird to regurgitate. So it's a bit more invasive. it does get some really important information, but if we can do that in a way which doesn't involve handling a bird and disturbing, then it's much better.
So the bits of DNA that are coming through in the poo, then, there must be the bits that they haven't digested as well, is it?
It's actually it's what they have digested. So coming through in the scat, it's trace remains of the food that's been consumed. So you don't get any hard parts anymore. You just get, if you've seen a bird poo, it's very much liquid with a little dark lump, and that's the bit we're going for. So if you think of it as the poo and the wee of the albatross scat coming out there, and that dark bit is the poo, and from that we can actually get the prey information through the DNA, so no hard parts at all.
But which albatross are you studying? Like, what's this particular species you're looking at?
Oh, I'm looking at 2 species for my PhD, but hoping to apply this technique across any species that people are looking at. But at the moment we're looking at the shy albatross, which is endemic to Tasmania, and then the black-browed albatross, which breeds circumpolar around the Antarctic on subantarctic islands. So trying to get an idea of whether we can apply this technique sort of at a local scale where we've got a lot more information about the fish and the species they might be eating, and then at a broader scale working with about another 9 institutions across the world.
Okay, when you say endemic to Tasmania, what does it mean? It stays around Tasmanian waters and islands?
Yeah, that's right. So the shy albatross breeds just in Tasmania, so nowhere else in the world. They breed on 3 islands off Tasmania, 1 up in the northwest and 2 down in the south. And so that makes them quite special to Australia, but also, given the small breeding population and only 3 locations, it does cause issues with population status. If there's anything that's going to affect them, then it could affect the whole species, which for a broader ranging species, that's less of an issue. But when there's only a small population, it can be really a large impact if something affects them.
Yeah, what sort of effects are you talking about that you're looking out for?
Well, there's a couple of things. So albatross tend to have quite a history of interactions with fisheries, so whether that be being caught on lines or caught in the trawl, or even just overlapping with the fisheries in the same food that they're targeting. But one of the biggest issues of late is that of climate change. So albatross are restricted in how far they can go from their islands because they have to come back to feed the chick at the nest there. So the food availability around these islands is predicted to change with ocean warming. And as that prey abundance and availability changes, so the albatross have to adapt to the new prey coming in, and it's their ability and flexibility to adapt to the different prey items that will dictate how well they'll do as the climates change. And the shy albatross is on a fairly northern extent of albatross range. It is quite warm. So, yeah, it will be interesting to see how they go. And so far, a lot of the population information we've got shows that they're actually declining in the number of breeding pairs and also the breeding success. So that's a bit of a worrying sign here in Tasmania.
Right. So this technique sounds like it's a pretty good new technique for examining the albatross, but you've done this on other species of seabirds before. Is that correct?
Yeah, that's correct. So we've used it on particularly penguin species. So through the Australian Antarctic Division, we're doing some work on Adelie penguins in Antarctica, finding out what they're eating. And also this has been applied by the same group to seabirds on Macquarie Island. And so the purpose of the Macquarie Island work is to look at not just an individual species, but look at a broad range of species on the island to find out what's in the waters off Macquarie. So it's looking at it from sort of a large ecosystem approach.
So you collected a lot of poo on a lot of islands around the southern waters?
I collect a lot of poo to get where I am. So yes, it's it's taken me to some pretty amazing places, and it's a good technique because you can do it in conjunction with other programs that are running. So you can be doing pond monitoring, census work, studies on which birds have come back to breed and so forth, and you can just opportunistically collect these scats as you're out there. So it's a nice technique. It doesn't require a suite of extra skills, but it just requires a keen eye for a poo out there in the colony.
Right, and something that I'm sure you have developed. Now,
yeah, over the years I've got a keen eye now.
Great. Now, I understand that you've recently published a paper where you've talked about using this technique as a way to get more data on albatross diets, and that there is a need for this in terms of, I guess, the different albatross species around the world. Can you tell us a bit more about that?
Yeah, look, we did a review on some of the methods used to assess albatross diet, and like I said, with these changes in climate and also the interactions with fisheries, being able to identify what they're eating and their resource requirements and monitor that over a long period is really important to establish how they're affected and if there's anything we can do to sort of mitigate the effects of climate change. And so we're looking at these different methods. We've found that there's actually been a reduction in a number of studies over time. And a lot of that is moving away from these more invasive techniques. They also cause a bias towards prey items that have hard parts, so squid beaks and fish bones. So it actually means that you don't detect things like gelatinous prey, so jellyfish and the like, which might be in the diet. So the DNA work with the scats might be an opportunity to integrate that with some of the techniques that used to be used, and also stable isotopes, which is where you're looking at chemical signatures in the feathers and blood to find out what they've eaten. And so using this in collaboration with some other people using different techniques, we can actually continue to monitor diet and get the really high information on prey so that we can actually monitor them and see what's happening over a long time period.
Fantastic. And have you learned anything new yet?
Actually, we're getting some really exciting information through from the black-browed albatross, and that's showing that jellyfish is a fairly important prey item in their diet. Now, whether this is that they're eating more jellyfish or whether it's now that we're just detecting it, it's hard to know. So like I said in previous work with regurgitates, you didn't get any information on gelatinous or soft-bodied prey, and now we're starting to see that jellyfish is an item that they're eating, and that makes sense. Albatross often go for things that are on the surface, which is why in the Pacific you have such an issue with plastics. And so jellyfish are there and they're visible and they're something they can eat. We're a bit confused as to why jellyfish. They don't seem to have a lot of nutritional value, but it could be something that it's opportunistic and it's there and
easy
they
to
snap
spot.
it up.
Now, I just want to ask you about, you said that the albatross numbers are declining. If people want to support the shy albatross and other Tasmanian albatross, how can they do that?
Yeah, look, one way they can do it is they can find out some more information on the shy albatross through a fund that was recently started up by Dr. Rachel Alderman in collaboration with the Bookend Trust and the Pennicott Foundation. And that can be found online if you look up the Tasmanian Albatross Fund. And that's got some more information about the albatross, what monitoring is being done, and they're trying to raise funds to continue that monitoring going into the future so we can start to look at long-term programs and continue these long-term programs going and try and protect this species.
Great. Well, thank you very much. That was Julie McInnes from Tasmania's Institute for Marine and Antarctic Studies. Thanks again for talking to us, Julie.
Thanks a lot, Chris.
That's all we've got time for on this episode of Lost in Science. Thanks for tuning in and joining us. Lost in Science is recorded at the studios of 3CR in Melbourne and broadcast across Australia on the Community Radio Network with the financial assistance of the Community Broadcasting Foundation. If you want to talk to us, talk back to us, you can get in touch. We have a Gmail account, lostinsci@gmail. You can also find us on Twitter and on the Facebook. And if that's not enough Lost in Science for you, you can always tune in again next week where the team will once again get Lost in Science!
Thanks for listening to a 3CR podcast. 3CR is an independent community radio station based in Melbourne, Australia. We need your financial support to keep going. Go to www.3cr.org.au for more information and to donate online.